operational properties, part 1. This section talks about how to find the Laplace transform where there's a translation or a shift of the graph with respect to S. If you look here, you can find the Laplace transform of S, but what about the Laplace transform of S minus A? Well, with here, that's said to be just a translation there to the right. And if it's S plus A, that becomes S equal to negative A, then that's a translation of S to the left from A. So what we are talking about basically is how to find the Laplace transform of e to the at times some function f of t, which is basically said to be the Laplace transform of f of t, and then with the translation where s goes from s to s minus a. So look how this theorem is easily calculated. Notice that this is the same. So you want to compute this Laplace transform. It becomes the Laplace transform of this f of t. The translation or the shifting is with respect to e to the at. So basically, anytime you have a Laplace transform and there's a combination of e to the at and f of t, you can think about it almost like back in algebra where you have the composition of a function, a composition of f and g. So it looks like f composed with g is f of g of x. And so that's what's happening. We take the Laplace transform of f of t, and then when you get that result, you just shift s from s to s minus a. Let's see. So this right here is the Laplace transform of t, and here the s is shifting from s to s minus 10 because of this e to the 10t. Remember, the Laplace transform of e to the 10t is 1 over s minus 10. So you first find the Laplace transform of this function t. So that's going to be 1 over s squared, and then s goes from s to s minus 10. Oh boy, talking too much. So here, this is just 1 over s minus 10 to the second power. So you see there's a couple of things going on, right? You see in that the Laplace transform of t which is 1 over s squared, and then you also see the Laplace transform of e to the 10t, which is 1 over s minus 10. Now, isn't this answer here, it's the composition of these two functions. So that's what's happening there. The same thing here. We look at the Laplace transform of t to the third, and then as s goes from s to s here, plus 2. This is e to the minus 2t. So this is 3 factorial is 6 all over s to the fourth, but then s goes from s to s plus t. I'm just going to write this, and then, hereafter, I think you get it. So replace the s with s plus 2. So we get here 6 all over s plus 2 to the 4th power. Now, we just have to just do our algebra here to simplify this. So this is t times, we're going to square e to the t plus e to the 2t. So this is e to the 2t plus 2 times e to the t times e to the 2t is e to the 3t plus e to the 4t. And so now we keep simplifying. This is the Laplace transform of t times e to the 2t plus the Laplace transform. The Laplace transform is linear, so we can break this sum into its parts. So the Laplace transform of the sum is equal to the Laplace transform of the parts. So this is t, that was a 2 there. You could have written it out in the front. Let me do that. So this is 2 times the Laplace transform of t times e to the 3t plus the Laplace transform of t times e to the 4t. And maybe by now you get it. So this is the Laplace transform of t, which is 1 over t squared, 1 over s squared, but s goes from s to s minus 2. So we're going to say s minus 2 to be squared, plus a 2 there, right? And then this is times 1 over s minus 3 to the second plus 1 over s minus 4 to the second. And we can write this 2 here times the 1, just say it's 2. Okay. So this one here, this becomes the, let's take the Laplace transform of sine 3t. Well, that becomes 3 all over s squared plus 9. But here, this is as s goes from s to s minus 1 because of this term there. So this is 3 over, wherever I see s, I'm going to write s minus 1. So this is s minus 1 to be squared plus 9. Okay. So let's continue. So we're going to use the linear algebra nature of the Laplace transform. So this is the Laplace transform of cosine 5t minus the Laplace transform of e to the t times cosine 5t plus 3 times the Laplace transform of e to the negative 4t times cosine 5t. Now there's no first translation theorem here because there's no e to the t associated with this. So this is just the Laplace transform of cosine 5t. If it's cosine, then you know an s goes in the numerator. So this is s over s squared plus 25 minus, here we do the Laplace transform of the cosine 5t, which is s over s squared plus 25, but there's a shift as s goes from s to s minus 1 because of this e to the t. This is plus 3 times, just do it like that, this is s all over s squared plus 25, but s goes from s to s plus 4. So the first one stays the same, so this is just s all over s squared plus 25. This is minus, wherever I see s, I'm going to write s minus 1, so this is s minus 1 over s minus 1 to be squared plus 25 plus 3 times, this is s plus 4 over s plus 4 to be squared plus 25. Okay, well, let's continue. Let's see here. The inverse form of just that first translation theorem. And so in other words, if you see the result, then how do you get back? And so this is the inverse transform of the first translation of a Laplace transform. And so that becomes, well, it becomes just the product of two things. It becomes the product of an e to the at and then times the original function. And once you see that, once you see the two functions operating there, then you write your result as the product of the two. Let me show you. And if you look at this, this guy is using two things that are going on here. One is I see the Laplace transform of e to the negative 2t, which is 1 over s plus 2. You see that, right? So that's one. And then number two, you want to be able to see the Laplace transform. It looks like t to the second, which is 2 all over s to the third. But there's no 2 there, right? No. There's no 2 there. So what is that saying? This is saying, this implies that 1/2 times the Laplace transform of t squared is equal to 1 over s to the third. Well, by golly, we have the answer. The answer is, oh, sorry, that's already there. The answer is this guy here and that number times that. All right. Now I'm going to, let's just say it like this. If you see the two functions, e to the negative 2t, and then also 1/2 t squared, I mean, that's the answer, folks. I'm going to write it out. This the answer, not in red. This is 1/2, that 1/2 here, t to the second times e to the negative 2t. And that's it. Now how do we get that? Well, remember, this is the inverse. So this is the inverse of, you have this this original function, which is this t squared. You have that guy operating in there, and so we're looking at this inverse of 2 over s to the third, but you don't have a 2 there, so that's why that's going to become a 1/2. And then s here, there's a translation on it where this s is actually s plus 2 goes back to s. So this is this 1/2 t to the second, and then you have this guy, this first translation, which is times e to the negative 2t. Now, the way I do it is, and it may be unconventional, but when I see the two functions operating, I know the answer is just the product of those two guys. And so I don't go through this last line here. That confuses me. All I do is I take what I have in red, and that's my answer. Let me show you with the next problem and see if I can try to make it a little bit more user-friendly. Now, this raises something that we hadn't seen yet for the Laplace transforms, and that is, it looks like I need to factor that denominator, but just factoring that out straight outright without having any rational values or even irrational values. To avoid that, we can complete the square. So this is the Laplace transform of 1 over, this is s squared minus 6s. Take half of the negative 6, we get negative 3. Square that, we get 9. So you're going to add a 9 and subtract a 9 right there in the same area, plus a 10. So this is the inverse transform of 1 over. Now these first three terms you can factor. That's just s minus 3 to be squared. And then we just add negative 9 plus 10. We get plus 1. Well, since there's a 1 up in the numerator, we're thinking either about cosine or sine. And so note, just remember that the Laplace transform of, let's say, for example, cosine kt, you remember that's s over s squared plus k squared. Well, there's no s there. And then the Laplace transform of sine kt is k over s squared plus k squared. So this k would be the 1, right? And then I have an s, but I also have a translation of this s minus 3. So two things that you see here. I see the Laplace transform of sine of t. Now what is that? That's 1 over s squared plus 1. And secondly, I see the Laplace transform of e to the 3t, which is 1 over s minus 3. So this answer here simply becomes, it's this sine t times e to the 3t, and you're done. See that? Once you see the two compositions of the Laplace transforms, then you can easily write your answer. So our answer here, and the answer to what? The inverse transform of 1 over s minus 3 to be squared plus 1 squared, and that's equal to e to the 3t times sine t. Okay? So that's not bad. Well, let's continue. So again, we're going to complete the square. This is the inverse transform. This is s up there. This is s squared plus 4s. Take half of 4, we get 2. Square that 2, you get 4. We're going to add a 4 and subtract it, the same term, and then plus the 5 there. So this is the inverse transform of that s up top. This downstairs becomes, looks like s plus 2 to be squared, then plus 1. Since there's an s up there, then for here, we're thinking cosine. Remember we talked about if there's an s in the numerator, then we're thinking cosine. If there's no s, then we're thinking sine. Right, so it's an s there. But notice this translation has s plus 2. So I got to have, if I'm going to have s plus 2 here, wherever I see s, I got to have the same thing, s plus 2. So we're going to manipulate it. We're going to add in there a sophisticated 0. So this is the inverse transform of s plus 2 minus 2 all over s plus 2 to be squared plus 1. So this is the inverse transform of first s plus 2 all over s plus 2 to be squared plus 1. And then this is minus 2 times the inverse transform of 1 over s plus 2 to be squared plus 1. So two things that I see operating with the first inverse transform. I see the Laplace transform of cosine t. Now what is that? That is s over s squared plus 1. Then I also see the Laplace transform of e to the negative 2t. Well, what is that? That's 1 over s plus 2. So here, this inverse transform is identically e to the negative 2t times cosine t. And you come over here, and what do you see? For this, there's no s in the numerator, so there we're thinking about a sine. So the Laplace transform of sine t is equal to 1 over s squared plus 1. And then you also see that translation, the Laplace transform of e to the negative 2t, which is just 1 over s minus 2. So from that, we build the answer. So the answer for the first part is e to the negative 2t times cosine t. And then minus 2, don't forget that, minus 2 times e to the negative 2t times sine t. Again, this is really some solution to a differential equation. Right? Really cool stuff. Well, let's look further. Let's look at this one. Well, that s up top throws us off, and we got this s plus 1 to the second. And so you think, well, do you complete the square? No, it's kind of already done for you in that denominator if you think about it. But whatever you put with that doesn't really give you a meaningful result. And so what I'm thinking is s plus 1 to the second in my denominator. Let's use partial fractions decomposition, see if we can break that down. So this looks like the inverse transform of some a over s plus 1 plus the inverse transform of b over s plus 1 to be squared. The s, again, throws us off. If it was just 1 over s plus 1 to be squared, then we can easily get that. So, and all I've done was just to look at s over s plus 1 to be squared is equal to a over s plus 1 plus b over s plus 1 to be squared. Well, this gives us, multiply both sides by the LCD, s is equal to a times s plus 1 plus b. Now, if you let s equal to -1, this implies that we have -1 is equal to b. And then do you see that a is equal to 1? And look, this is s is equal to a times s plus a plus b. Just simplify that out. Now, equating corresponding parts, and this is from this statement here, you get s is equal to as, right? S is equal to as, and 0 is equal to a plus b. Well, if s is equal to as, then that just means that 1 is equal to a. And if 1 is equal to a, then -1 is equal to b, but you already got that. So all we just needed was a. So we have the inverse transform of a, which is 1 over s plus 1, right? Plus the inverse transform of b, which is -1 over s plus 1 to be squared. Well, let's see. This first part, there's nothing special about that. There's no combination of, no first translation theorem. It's just the inverse transform. So this is just e to the -t. And then -1, minus that minus there. And so this is two parts. This is an e to the -t. I see that. But then I also see a t, right? Look, this guy, I see two things. I see the Laplace transform of e to the -t. Well, what is that? This is 1 over s plus 1. Okay, you see that. And then number 2, the Laplace transform of t. Well, what is that? That's 1 over s squared. You get that. So, do you see that this result is the solution to a differential equation where the one answer, e to the -t, repeats? You remember, for u is e to the -x. It repeats, and so they supply an x term times it so that the solution is linearly independent. Well, here x is t. Okay, very good. Just trying to enunciate. All right. Okay, and you can do that last one. I have a lot of problems here to do. And so, yeah, a lot of problems. And it's making my neck hurt because I'm having to sit down in this chair to work these problems. And oh, mercy. Okay, so this problem we want to solve using Laplace transforms. You can solve it from a previous method. You get the same thing. Pretty neat to look at, to compare both. So we take the Laplace transform of y prime plus 4y, and that's equal to the Laplace transform of e to the -4t. Just take the Laplace transform on both sides. I guess we better use the black instead of the blue. So this is the Laplace transform of y prime plus 4 times the Laplace transform of y, or that's just y of t, just shorthand, just y, is equal to the Laplace transform of e to the -4t is 1 over s plus 4. So this is the Laplace transform of a derivative, so this becomes s times y of s minus y of 0 plus 4 times y of s is equal to 1 over s plus 4. factor out the y of s, right? And oh yeah, y of 0 is 2, right? So this is s plus 4 minus 2 is equal to 1 over s plus 4. So just come here. This implies that y of s times s plus 4 is equal to, add the 2 on both sides. This is 1 over s plus 4 plus 2. Now let's simplify that right side. This is y of s times s plus 4 is equal to 1 over s plus 4 plus 2 times s plus 4 all over s plus 4, which is 2s plus 8 plus 1 is 9 over s plus 4. And so the y of s, now we divide both sides by s plus 4. This is 2s plus 9 all over s plus 4 to the second. Take the inverse transform of both sides. The inverse of y of s is just y of t. Because remember, y of s is already the shorthand for the Laplace transform. So you get y of t, which would be the answer, like y of x, for old-fashioned differential equations. But we come up to the modern world where the true value for x is actually t, to represent maybe some function with respect to time. This is the inverse transform of 2s plus 9 all over s plus 4 to the second. Now, there's a lot going on there, and we're just halfway done. So we're going to use here partial fractions decomposition to break that down. So we have 2s plus 9 all over s plus 4 to the second. So this is a over s plus 4 plus b over s plus 4 to the second. I guess I can make my 9 a little bit better and improve on the 2 to the best of my ability. Now we simplify this. So this is 2s plus 9 is equal to a times s plus 4 plus b. So we let's let s equal to 4. That'll get rid of the a. So this implies that we have 2 times 4 plus 9, negative 4. Two times negative 4 plus 9. That's that left side. Don't need parentheses there. Is equal to that a times negative 4 plus 4 plus b. So this implies that b is equal to 1. Now we need to solve for a. Let's look at that. Don't have any more let statements anymore because there was only one factor for s. So this is 2s plus 9. Simplify that. The right side. If you look at it, if you know what's going on from algebra days, 2 is equal to a. But I'll write it out. This is as plus 4a plus b. We let corresponding terms equal. So that is, we let this guy equal to this, and then the constant equal to the constants over there. All we're looking for is a. So see how you get 2s equal to as, so a is equal to s. So that implies that a is equal to s. If we didn't use this previous method for b, then you could say and 9 is equal to 4a plus b. So you would take the, a is equal to 2. 2s equal to as, so a is equal to 2, not a is equal to s. I'm making a donkey out myself. So a is equal to 2. So if we didn't have this previous method, let a equal to 2 here, you get 4 times 2 is a, 4 times 2 is b, 4 times 2 is 8. So then you subtract 8 on both sides, 9 minus 8, you get b is equal to 1. But we don't need that because we got it already up there. All we were looking for was the value for a. So now we go back upstairs to here, and we broke down that part on the inside by this expression, right? So what that gives us is y of t is equal to the inverse transform of a, which is 2 over s plus 4, and then plus the inverse transform of b, which is 1 over s plus 4 to the second. What is that? S plus 4 to the second. Okay. So y of t, our answer, is just 2 times e to the negative 4t. Remember, this is a combination of two functions, right? The first one you see is the e to the negative 4t, but then you also see a t, right? Because the Laplace transform of t is 1 over s squared. And this is, again, see how this is the solution for a differential equation? I mean, this was the differential equation that we solved. We solved it using Laplace transform. Now, what's so cool about that was this guy had a repeating answer. Now, why do we get two answers? You remember, first you solve for the homogeneous differential equation, set that equal to 0, and you get a solution. Then after that, you solve for the non-homogeneous differential equation, and then using the initial condition. Pretty cool. Notice that the solution for the non-homogeneous part also had an e to the negative 4t, but it was repeating, so we had to fix that. And Laplace transform automatically fixes that glitch by supplying, previously it's an x, but here it's a t. It's the same thing. So let's look at, I'm going to do one more here for you, and then we'll look at the last part of this section. You have that problem, and then we have this one. I'm going to do this one. I think this number is a little bit more difficult than this guy right here. Why is 26 more difficult? Because 26, I think it was 26, 25 is a non-homogeneous differential equation. This is just a homogeneous differential equation. Okay. So we take the Laplace transform of both sides. I'm going to go ahead and just break this up into parts. Minus 6 times the Laplace transform of y prime plus 9 times the Laplace transform of t is equal to the Laplace transform of t. So this first part is s squared times y of s minus s times y of 0 minus y prime of 0. That's the first part. Then minus 6, put that in brackets, the Laplace transform of y prime, that's s times y of s minus y of 0. And that's all that's there. Plus 9 times this guy is represented by y of s is equal to 1 over s squared. That's the Laplace transform of t, remember? So now let's plug in our initial conditions. minus s times y of 0. Y of 0 is given to be 0. Minus y prime of 0, that's 1. Minus 6 times s times y of s, that's an s. Minus y of 0 is 0. Plus 9 times y of s is equal to 1 over s squared. Okay, so now I'm going to get my y of s's together. That's times s squared minus 6s plus 9. That matches up, right, with y double prime minus 6y prime plus 9. The s kind of replaces the y primes in some kind of sense. Now what I have left, once I factored, it was 1, 2, 3. So I have, this is s times y of 0, excuse me. Oh yeah, y of 0 is 0. So this is just s times 0 is 0. I thought it was like s of 0. What function is that? Okay, anyway, I didn't eat my turkey sandwich. So this guy is just 0. So I don't confuse myself. So 1, 2, 3, 4 terms. 1, 2, 3, and then that 1 there. I'm going to add that 1 to both sides. So this is equal to 1 over s squared plus 1, which is 1 plus s squared over s squared. Okay, so this is now y of s. Why is my neck hurting? Times s minus 3 to be squared is equal to 1 plus s squared over s squared. This s squared minus 6s plus 9, just factor that. So now we divide both sides by s minus 3 to the second. So this is y of s is equal to, just write that as s squared plus 1 over s squared times s minus 3 to the second. So now we take the inverse transform of both sides. So this gives us y of t is equal to the inverse transform of s squared plus 1 over s squared times s minus 3 to the second. I need to simplify that. And maybe I should have done that first, but it's okay. So this is the inverse transform of s squared over s squared. It's going to be a lot. So y of t is equal to the inverse transform of s squared over the denominator s squared times s minus 3 to be squared. And then this is plus the inverse transform of 1 over s squared times s minus 3 to be squared. And let me take this sweater off because I'm getting hot. Alrighty. So now that first part, good thing for us is that s squares cancel out. Good. So we get y of t is equal to the inverse transform of 1 over s minus 3 to be squared. Two things going on there. Now that other part over there, man, we got to use partial fractions to break that down. Why, you know? Couldn't life be so much easier? Well, life is not, so This is good. Now I'm going to go ahead and get this first part. So this is y of t is equal to, now notice there's two things going on here. There's a t, and then there's also an e to the 3t times t. That's for that part there. That's the inverse of the first translation theorem. Now this next part takes some time. You know, this is like one that like I don't do, but then, you know, when you start working the problems in web assign, you have one just like it. So now you got me. So this is the first part is already done. So now we work on the second part. So for that second part, we're going to use partial fractions decomposition to break it down. This is a over s plus b over s squared plus c over s minus 3 plus d over s minus 3 to the second. Multiply both sides by the least common denominator, so you end up with 1 is equal to a times s minus 3 to be squared plus b times s minus 3 to be squared plus c times s squared times s minus 3 plus d times s squared. Now we can only let s equal to 0 and let s equal to 3, but we can still have two more generic terms to solve. We just use the old method that we used in high school. This is an s. Boy, these s's look funny. So let s equal to 0. Let's see what happens. So end up with 1. That s0 there is going to cancel this out. A goes out, c goes out, and d goes out. So I have left, if s is equal to 0, I have b times this negative 3 to the second. So that implies that b is equal to 1/9. Secondly, let s equal to 3. And that implies that 1 is equal to, now if s equal to 3, 3 minus 3 will cancel out the a, cancel out the b, cancel out the c, because you have a s minus 3 there. All you end up with is this d times 3 to the second. So that gives us here, d is also 1/9. Now to get the other parts, we have to just use algebra. And as Dr. Stallworth used to say, just apply brute force. Man. So this is I'm going to take this equation and just expand. So this is a times parentheses, it's going to be s squared minus 6s plus 9, each one times s, so that's s to the third minus 6s squared plus 9s plus b times parentheses s squared minus 6s plus 9. Then this is plus c times s to the cube minus 3s squared plus ds to the second. Okay, so now what I'm going to do is get the corresponding terms together, get the s to the third powers together, get the s's to the second powers, just equate those, s's to the first power, and then the constants by themselves. So the only time that I'm going to get a number on the left side is going to be 1 equal to the constant terms. Everything else in terms of s to the third, well, there's no s to the third on the left side, so I'm going to get 0 is equal to a times s to the third plus cs to the third only have two of those guys. And you don't even have to write s to the thirds because you just divide that out. So all you have is just really a is equal to, or 0 is equal to a plus c. Now you go to the s to the second, you get 0, find the s's to the second power. Right? So I'm not going to write s to the second because it's going to be redundant, but I get 0 from the left side because there's no s to the second over there, is equal to, this is negative 6a plus b minus 3c plus d. Now the cool thing is I know b and d, but I still don't know a and c. Now I can plug in b and d and get two equations with two unknowns and solve, just using matrix, simple matrix. But that's fine. I'll leave that as it is for right now. Now let's go to the s to the first powers. So just have that. So that becomes 0, and for the s's to the first power, this is 9a equal to 9a minus 6b. Minus 6b. Now that's good. I can use that. And just as we continue in this Phantom of the Opera, what about the constant terms? 1. Look at 1 is equal to just the terms where there's no s's. Well, there you go. So that's 1 is equal to 9b. But you knew that b is equal to 1 over 9. We already got that, so we don't need that guy. So, but since we know that b is equal to 1 over 9, I can solve here. So here I get 9a is equal to 6b. 9a is equal to 6 times b is 1 over 9. So this is 2 over 3. So a is equal to 2 over 27. So I got a is equal to 2 over 27. If a is 2 over 27, that means that c is the opposite of it, right? Because c is equal to negative a. Negative 2 over 27 for c. So I get c, negative, b, d, and a. So now we can write our answer. What is it? That's, that's what my middle scientist say when he was very small. So we're looking at this y of t so y of t is equal, that first part we already solved. That was e to the 3t times e to the 3t times t. Then now it's plus all of this stuff that we broke up. So this is plus the inverse transform of a over s plus b over that plus c plus d. So it's a, and we got a. A is 2 over 27. That's over s, right, plus the inverse transform of the b, and the b we got to be 1 over 9. let's see here for b, that's over s squared plus the inverse transform of c. C is that -2 over 27 over s minus 3 plus the inverse transform of d, and d is 1 over 9, and that's all over s minus 3 to the second. Need more space. I wrote too big over here. Oops. So let's see, this was the inverse transform of a, which is 2 over 27 over s plus the inverse transform of b, which is 1 over 9 over s squared plus the inverse transform of c, which is -2 over 27 over s minus 3 plus the inverse transform of d, which is 1 over 9 over s minus 3 to be squared. Yep, is that right? So good. So then we write the answer. So y of t is equal to, you got that e to the 3t. Oh, it's too big. E to the 3t times t, and then this is plus 2 over 27. The inverse transform of 1 over s is just 1, so that's fine there. You move over, plus 1 over 9. The inverse transform of 1 over s to the second is just t, and then this is plus, or minus, that's a minus 2 over 27. This is a minus 2 over 27 times e to the 3t, which repeats itself here, so that's where it's applied a t times that, right? T totally right. Okay, then this is plus, see that 1 over 9. This is a combination, composition of two Laplace transforms. What do you see there? I see e to the 3t and also t. Now that's interesting because that e to the 3t times t is also repeating over here, so we got to combine them. Oh boy, now that is pretty interesting. Oh, that's fabulous. So we need to, in order to prevent the solution from being linearly dependent, if you will, we need to be able to write that in its correct format, and that is that y of t, I have to add these two terms. So this e to the 3t times t times 1/9 e to the 3t times t is 1 plus 1 over 9, right? So you see that you get this 1 plus 1 over 9 is 10 over 9. So our answer is 10 over 9 times t times e to the 3t plus 2 over 27 plus 1 over 9t minus 2 over 27 times e to the 3t. That's a lot going on there, right? So let's see a little bit further. And you get down to the unit step function, which ideally for engineering problems that deals with signals, this becomes like over half of what you would do, and I'm already tired. So sorry, but no, we're good. The unit step function is a signal. It turns on, it turns off. It says that the unit step here for t minus a is defined when t some time interval is less than a, you turn the function off with by 0. If t is bigger than a, then you assign it 1. Now, to get any kind of function you want, you just multiply any kind of function you want times this unit step function, and you can turn on and turn off whatever function that you supply. And so that's just a simple graph of just the simple unit step function of 1. Now, in terms of the Laplace transform, we call this the second translation theorem, and is based on basically the Laplace transform of a function that's being turned on and turned off by a unit step function is equal to e to the negative as times the Laplace transform. Okay, and then if the function is just 1, then the Laplace transform of that unit step comes out to be this right here. So note here that f of t is 1. And so the Laplace transform of 1 is 1 over s, and that's how you get the s in your denominator. So we're going to use that to our advantage, use this theorem, and then they're going to reverse it and do the inverse of that. And then that's when you really want to, just, I don't know about scratching your hair out, or just plucking your head off. So that's the inverse, and we'll get to that one when we see problems like that. So first, just very straightforward. Two things that you want to be able to identify with these problems, and one is what's the value for a? What am I talking about? Let's go back up here. You see, this unit step defines it by some pivot value of a. So what is a? And then secondly, what is the function f of t? And with that in mind, then you'll be able to write your answer in a format like this. So what is a, and then what is f of t? So here, a is equal to 1, and then 2, f of t. Now, f of t is just t. See, this is t minus a. So f of t is t, right? So this value has to be e to the negative as, where a is 1, times the Laplace transform of t. And so this is just e to the negative s times 1 over s squared. So this is e to the negative s, and then the Laplace transform of t is just s squared. Now, the definition for the unit step, the Laplace transform of unit step, calls for this translation of, if I'm looking for the unit step of t minus 2, then I need to be able to see the function translated as well. So I don't see that, so we supply it. So this is the Laplace transform of t minus 2 plus 2 times the unit step of t minus 2. which becomes the Laplace transform of t minus 2 times the unit step of t minus 2 plus 2 times the Laplace transform of, this is really like 1 times the unit step function of t minus 2, which you can do that. This is just an on and off. T values bigger than 2 is 1, t values less than 2 is 0 for that one over there. This one says values of t is greater than 2 or equal to 2, then we turn on the function t minus 2, and then if it's less than 2, then you get 0. So two things you want to identify, and that is, what is A? A is 2, then secondly, that's not supposed to happen. What's the function? It's t. Now over here, the same thing. What is A? 2. And what's the function? F of t is equal to 1. Right? So for the first part, this is based on how it's defined. This is e to the negative as, e to the negative 2s times the Laplace transform of t, right? Plus that 2 here times e to the negative 2s times the Laplace transform of 1. Now you work that out. Well, the Laplace transform of t is just 1 over s squared. So this is e to the negative 2s over s squared plus 2 times e to the negative 2s over s. Laplace transform of 1 is just 1 over s. This is a negative, not a comma. Okay? So, as we move a little further, let's see if we can take another problem. I think I have one down here. Again, something similar. Notice this is cosine 2t, but over here is just t minus pi. So we need to supply here a very equivalent form. So we have cosine of 2t, and then this is going to be minus 2 pi, but plus 2 pi times the unit step of t minus pi. Okay. So let's see. I'm going to break down this cosine of 2t minus 2 pi plus 2 pi. I'm going to treat this as cosine of u plus v. U is 2t minus 2 pi, and v is 2 pi. So this is cosine of 2t minus 2 pi times cosine of 2 pi plus just the double angles, whatever, you know, from trig. Who remembers that, right? So this is sine of 2t minus 2 pi, and then times sine of 2 pi. Now cosine of 2 pi is just 1. And sine of 2 pi is 0. So this expression here is just cosine of 2t minus 2 pi. That's exactly what it is. So we have the Laplace transform of cosine. All you need is 2t minus 2 pi times the unit step of t minus pi. And you say, what about the 2? And there's over here for the unit step, it's just t minus pi. Well, we'll take care of that. Let me show you. Two things you want to be able to identify. What is a? Here, a is going to be pi. Then secondly, what's the function f of t? The function f of t is cosine of 2t. Now that 2 there takes an account of everything you need. So this becomes e to the negative as negative pi s times the Laplace transform of cosine 2t. You got to work that out, right? Let's get this out the way. So your answer is e to the negative pi s. Now the cosine Laplace transform of cosine 2t is, remember for cosine you put an s in the numerator, so this becomes s all over s squared plus 4. Wow. That's crazy, right? Yeah. Now, about 3 more problems. This involves just the reverse of that by using the inverse of the second translation theorem. So translate that, just some more crap, right? So anyway, this is important stuff. Now, recall that we were talking about the Laplace transform of some function associated with a step function. Right? So this guy comes out to be e to the negative as times the Laplace transform of some f of t. What if they reverse that? So we talk about the inverse of that right side, e to the negative as times some Laplace transform of f of t, which is some capital Y of s, right? This guy has to be the inside over here, so this is equal to f of t minus a times the Laplace transform of t minus a. Okay. So still 2 things you want to identify, and that is what is a? A here is 2, and then what's the function that we're dealing with? What's f of t? Now f of t here, you get the idea that they're using this t squared. But watch this. The Laplace transform of t squared is going to be 2 over s to the third. I don't have a 2 in the numerator, so you better want to use 1/2 t squared. So 1/2 times the Laplace transform of t squared is equal to 2 over s to the third. So the function is going to be 1/2 times t squared. So let's write this answer. Again, the answer is going to be has to be written in this form. Now, I'm going to give you the formula sheet that has that, these formulas on there, so you have to memorize all that stuff because there's a lot going on for the Laplace transform. Even I know that. Do I have formulas to go by? No, because it's just me, right? You live and you sleep with this stuff, and so it just becomes a part of you. So this is the inverse transform of, this is just the problem, e to the negative 2s over s to the third. Now, again, 2 things you want to know. What is a? A is 2. What's the original function? It looks like initially it's t squared, but it's actually 1/2 t squared. Okay. So So let's see. We write this as the function f of t minus a. So wherever you have the t, you got to write t minus a. So this is 1/2. It's t squared, but it's going to be t minus 2 because a is 2 squared times the unit step of t minus 2. That's it. As Pepe Le Pew would say, no. Yeah. A lot of stuff going on there, right? Wonderful, wonderful. So now, let's look at the next one. I think it's just 2 more problems here. So this guy and this other one, and then, man, we're going to run for the hills, you know. So let's see. So 2 things I want to be able to pick out. One, what is A? A is pi. And then secondly, what's the function f of t? Well, I see a s squared plus 1 downstairs. So it looks like it's 1 over s squared plus 1. And so if that be the case, is that cosine or sine? Well, cosine has an s in the numerator. Sine has the k in the numerator. So this looks like it's going to be the sine of t. Very good. So if that's the case, then, you know, our answer has to be of the form some f of t minus a times the unit step of t minus a. All right, so let's see. The function is, this function f is sine t, but when I have t, I'm going to write t minus pi, and then times the unit step of t minus pi. So our answer is sine of t minus pi times the unit step of t minus pi. Now, I'm good with that answer, and if you plug that in, I'm cool with that. Now, I wonder if Weber-Sine would take that. Because, I mean, this answer in Weber-Sine does not say that. The answer is like negative sine t, I think is how they said it. And then I realized that they were using, again, those sine of the double angles and that kind of stuff. So let's see. So recall sine of u plus, well, this is minus, so use the minus. Why does life have to be so hard? So this is sine of u cosine v minus sine of v cosine of u. So let's see if we can put that into perspective. So this is sine of t minus pi is sine of t cosine of negative pi minus sine of negative pi. Oops, we don't bring the sign over, I'm sorry. Oops. Pi. The sign is brought over here. Sine of pi cosine of t. So sine of, that's how they get it. So cosine of pi is -1, and then sine of pi is 0. Oh, interesting. So this is just stupid sine t, right? So, oh, negative. So this is negative sine t times the unit step of t minus pi. again, I mean, if you give that to me, then that's okay with me, right? And Weber sign should take that. If you know, it should take that for the answer. Definitely, you know, either one is the answer. They simplify it further by using that stuff from trig. Who remembers all that stuff? So if you just give this guy to me that I have the first one that I got the okay by, hey, we're good, man. We're good. Now this last one, hopefully this guy is not as long, right? About to make me throw up. We got to use partial fractions. Let's do the partial fractions here separately first. This is a over s. Why is my head hurting? Plus b over s plus 1. So this is 1 is equal to a times parentheses s plus 1 plus b times s. If you let s equal to 0, then you get a is equal to 1. And if you let s equal to -1, you get b is equal to -1. Okay. So we can break this down. This is the inverse transform of the a over s. So it's going to be all that junk there, e to the negative s over s. Then minor this b minus 1. So say minus the inverse transform of e to the negative s over s plus 1. Okay. Now we can finish writing the answer. I can put the steps here. Two things you want to recognize. What is a? Well, here a is 1. And then secondly, what's the function? F of t is 1. Because the Laplace transform of 1 is just 1 over s. And then for this guy, it's the s. So what is a? A is equal to 1. And then 2, what's the function? F of t. It looks like e to the negative t. All right? So let's write our answer. Now again, we're looking for, this is the inverse of this e to the negative s over s, then minus the inverse of e to the negative s over s plus 1. So that first part is the function times its unit step. So the function is, we said, is 1, right? And then times its unit step, this is u of t minus 1. Minus this function is e to the negative t, but we have to write that t as t minus 1 times its unit step of t minus 1. Okay. And that's it. Man, let's go.